Uh, yeah, hello. Yes, please, any doubt?
Yes, actually, week 12 solved with a session video is neither available on calendar nor in the YouTube. Can you please update it?
Okay, week 12 solve with us.
Yes, Saturday.
Okay, who took the session? Do you remember?
Actually, Pulkit Pranjal Bhaiya has taken that session. So
Uh,
that session is actually only recorded, not streamed actually.
okay, only recorded. Okay, okay, thanks. So I will ask sir to send me the recording. Okay, then I will share it. Just a minute. Okay, so end term week wise weightage is 50 around 50% from the last 4 weeks, 9, 10, 11, 12, and the remaining 50% from the first 8 weeks. Okay, yeah. So today we will be doing week 9 revision, which is perceptron and logistic regression. So before going into that, anybody has any doubt? Hello, am I audible? Okay, thanks. Hmm, hmm, Okay, that- okay. So in the week 9, we will start with the linear classifier. Okay, and we have seen that a linear classifier H. Okay, in which we will take the data which is in RD, and our output either may be 1, -1, 0, 1 according to the label. Okay, where H is such a function W transpose X. That is, we are only taking the linear function into the account. Okay. So a general linear classifier will look like this, where we will have a vector W, okay, and we will draw a line which is W transpose X equal to 0. So this line is nothing but the perpendicular to the weight vector, okay, and the data points that will lie on the side of the weight vector in the direction of the weight vector will be classified as label 1, while on the other side we will classify it as -1 or 0. Okay, so this is the linear classifier. Now, our goal is to minimize the 0, 1 loss, that is the number of data points that are misclassified. Okay. Our predicted label is given by W transpose Xi, and Yi is the true label. Our goal is to minimize the 0, 1 loss, that is the number of data points that are misclassified. Okay. And as Prof has discussed from the starting of the classification problem in week 7, that minimizing 0, 1 loss is an NP hard problem. That is, it occurs in non-polynomial time. So we will put some constraint on the data and check whether it can simplify our problem or not. Okay. And what such assumption would be our linear separability. Okay. And one remark that for the rest of the document, we will assume that all the labels that lie in the set 1, -1, okay, and green data points will belongs to class 1, while red data points will belongs to class -1. Okay. So this was a little bit introduction before actually going through the week 9 concept. Okay. Any doubt till now? Okay. Then comes linear separability. So what is mean by linear separability? That if we have a data set x1, y1, x2, y2 till xn, yn, we will call this data set linearly separable if W transpose xi times yi is greater than equal to 0 for all data points, okay, where our labels are 1 or -1. Okay, this is same as that two classes are divided by some weight vector. Okay, and if we this was from mathematical point of view, and in simpler terms, a linear separable data set is that if there exists a linear classifier that perfectly classify or separates all the data points, and thus it produced zero training error. Okay, so just like this example, on the left hand side we have class red, which is on the left side of the linear classifier, and class green, which is on the right side of the linear classifier. So this classifier W transpose X equal to 0, that is this line, it perfectly separates both the classes. While one first known example of the linear separability is on the right hand side. You cannot draw any line which perfectly separates both the classes. You can try out with any line, it will not perfectly separate both the classes. So this is the example of non-linearly separable dataset, while on the left hand side is the example of the linearly separable dataset. Now, we could also have a situation where dataset is just about linearly separable. Okay. That is, there's only one linear classifier that perfectly separates the data. Okay. So that is here. Okay. Now, remember just from our course that we will always assume that our classifier line will pass through the origin until it is specifically mentioned in the question. We will assume that the classification line or the linear classifier line will pass through the origin. Okay. In general, it is not needed to, but from the course point of view, we will always assume that it will pass through the origin. Okay. So for the algorithm that is the perceptron, okay, we have to get rid of this limitation, that is our data set should not be just linearly separable like this. Okay, it should be linearly separable with some margin. Okay, and one note that for a data that is linearly separable with some positive margin, perceptron algorithm will always work. Okay, so that is the next point, that linear separability with some gamma margin. So a data set is linearly separable with some gamma margin if we can find a W in the same space in which our data points are lying and a gamma that is greater than 0, such that W transpose Xi is greater than equal to gamma for all the data points. Okay, and your labels are in 1 and minus. Okay, so a typical example for a linearly separable data set with some gamma margin. Okay, so this is our linearly classified boundary. This is the weight vector, and our data set is linearly separable with some positive margin. Okay, margin we will always take it as a non-zero positive quantity. Okay, till now is it clear for everyone? Okay, good. And small note that for linearly separable data set with a positive margin, we have algorithm that can return a valid classifier that achieves zero training error. So Perceptron, Logistic, SVM. Okay. Now we will go through the main actual algorithm, Perceptron learning algorithm. Okay. The prediction rule is simple, that if W transpose X is greater than equal to 0, then the predicted label of the data point would be 1. If it is less than 0, then the predicted label would be -1. Okay. One small thing that is about the tiebreaker case for the W transpose X is equal to 0. Okay. By default, we are taking it to the positive class. If it is mentioned in the question that uh, it is it can belongs to negative class, then take that. Okay. But if nothing is mentioned, by default, just take it to the positive class. Okay. Next. So there are 3 steps in Perceptron. First is we will initialize our weight vector. Okay. Generally, we initialize it to the 0 vector. Okay. In the same space in which our data points are lying. Okay. Unless it is specifically mentioned that you have to start your perceptron algorithm with some weight vector, we will initialize it to 0 vector. Okay. Unless it is specifically mentioned. Then until you find any mistake, that is the W transpose Xi is not equal to Yi. If any mistake occurs for any data point, then the perceptron update rule is we will add the data points time the label to the weight vector, and that new vector would be our will be used as the linear classifier. Okay, so this is the old vector. This is the data point for which the perceptron algorithm or the current weight vector is making mistake. We will add that, and the resultant vector would be our new weight vector that we will be using for classification. We will be doing this until there is no any data point for which it makes mistakes. That is, it achieves 0 error. Okay. A detailed explanation is first initialization of the weight vector. Then we will cycle through the data point in a fixed order. Okay. One small note, perceptron may return a different vector if you change the way you cycle your data points. Okay, just like if you are cycling the order in which it is given x1, then x2, then x3 till xn. Okay, then it might give a different vector. And if you cycle, let's say first x1, then x3, x4, x5, and x2, x7. Okay, so it is dependent upon the way you cycle through your data points. Okay, and based on the way you choose your data points, it might give you a different weight vector also. Okay, now if xi is a mistake, the update rule is just data points times the label added to the weight vector for which it is making mistake, and the new weight vector would be used for further classification. Okay, and if no mistakes are being made by the weight vector for n consecutive iteration, that is all the points are correctly classified with that current weight vector, then your algorithm terminates and you will get the weight vector which perfectly separates two classes. Okay, and the t is basically how many times the update happened to the weight vector. Okay, so some observations that we always begin with the zero vector. Okay, unless it is specifically mentioned, you will always begin with the zero weight vector. Okay, and as you iterate through the yes, Piyush, any doubt?
Let's say we have 10 data points, like
Mm,
number 1, 2, 3, up to 10. So
okay.
if the like perceptron, if the weight vector makes mistake at,
Mm,
let's say, third data point, then
mm,
we have to first update the weight vector, and then we have to go to like data point 4, right?
yeah.
Or we have
Mm,
to first, like, we have to complete the all the, like,
yeah. Yeah. Okay, there's one example, okay, in the below slides. From there you will be able to understand. But yeah, whatever you said is correct. Okay. If
like
the
whenever we will like encounter any mistake, we have to update at that point, and
mm,
with the updated vector we have to go to the next data point, right?
yeah, 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 and continue your cycle with the updated weight vector. Okay.
Okay, okay.
And you have to do it until all the data points are correctly classified with any weight vector. Okay. In the course of algorithm, that is when you are performing your algorithm, the number of mistake made is equal to the number of updates to the weight vector. Because whenever the perceptron algorithm will make any mistake, we will update the weight vector. So number of mistake is equal to the number of updates being made to the weight vector. While the number of iteration can be greater than or equal to the number of mistake. Okay, because there might be iteration in which there are no mistake, that is the final iteration. Okay, so number of iteration can be greater than or equal to the number of mistakes made. And the most important note is this, that for a linearly separable data, yes, Karthikeyan, doubt,
How it can be greater?
for the last iteration, okay, when it will not make any mistake, okay, then it will be greater, the number of iteration, because that one iteration will be more you have to make to confirm that yeah, no mistakes are being made. So now this is the point where your algorithm will terminate. Okay,
Or it is then it is always plus one. You
yeah.
mean to say? Okay.
Okay.
Okay. Thank you. Thank you.
We are only going to cover the week 9. Okay, for week 10 the tutorial video has been released. For week 10 you can watch that also to revise the SVM. Also we will be having week 10, 11, 12 combined revision, I guess on Friday. Okay, but till then if you want to revise week 10 the tutorial has, yeah, yes, doubt,
Sir, general doubt. Where can we get
yeah,
these PIQ revision slides, sir?
PYQ,
Yes, sir. PIQs
uh,
discussion
which,
slides.
I discussed yesterday, you mean?
Yes, yes, yes.
I have already uploaded that just after the session.
Sir, where it is, sir?
It is in the master folder in the live session slides. So, okay, if you, okay, I will share maybe in the live session slides. If you go to the TA notes, Okay, in that previous term discussion, and in that n term folder, you will find it. Yeah, yes, Karthike, do you have any more doubt? No. Okay. Just 1 minute.
No, no. Thank
Okay.
you.
1 minute. Let me plug. Okay. So we were discussing that for a linearly separable data set with some positive margin, the perceptron algorithm will always converge. Okay. Now we will study the proof of its convergence, but the proof will not be asked in the question in the exam, but you should remember the inequalities that we are using and the final result about the number of mistakes. Okay. These two things you should remember. Okay. For the exams, because some question might be asked from the inequality or maybe from the number of mistakes. Okay. So for the proof, we have to take some assumption into account. Our first assumption is that our data set is linearly separable with gamma margin. That is, there exists some gamma greater than 0 and W star such that for every point xi yi in our data set, W star transpose xi yi is greater than equal to gamma. And also the norm of the W star is equal to 1. Okay. Now, one thing that if you are able to find any weight vector which perfectly separate your data set, then you can always normalize your weight vector to have the norm of the vector to be 1, and this will not affect your final decision boundary. That is the boundary that you will get from the original weight vector and the normalized weight vector would be the same. Okay, so and the margin is the distance between the decision boundary and the closest point in the data set. Okay, so this was assumption 1, that our data set is linearly separable with some positive margin, and our weight vector has norm 1, that is, it is a unit vector. Okay, the second assumption is radius bound, that is, there exists some r greater than 0 such that for every point xi yi in our data set, the norm square of our data point is less than equal to r square. And what does this assumption make sense in geometrically, that all our data points lie inside some big ball of R. Okay. So this encodes the fact that all the data points are within a ball of radius R centered at the origin. Okay. And visually these two assumptions are look like this. Okay. Our data points are linearly separable with the gamma margin. Okay. Margin is the point which is closest to the decision boundary. Okay. And all the data points are lying inside some ball of radius r centered at origin. Okay. So these are the two assumptions that we needed to prove that the perceptron algorithm will converge if you have a data set that is linearly separable with some positive margin. So a little bit theory that we start with weight vector 0, and since each update to the weight vector happens after only the mistake is observed. Okay, and the mistake and update can be interchangeably. The case of t equal to 0 corresponds to the 0 update, and the corresponding weight vector would be W naught. Okay, and after t rounds, the perceptron has seen t mistakes and the vector has been updated t times. Okay, so just a little bit about the notations how we are using. Okay, t equal to 0 is the initialization, and after t rounds, perceptron has seen t mistakes and the weight vector has been updated t times. Okay. So we will try to bound upon the mistake. So first we will go with the upper bound on the mistake. So assume that the perceptron has gone through t minus 1 update, and then x be a data point which is misclassified by the current weight vector. Okay, that is wt minus 1. And what does it represent mathematically? That wt minus 1 x times y is less than equal to 0. Okay, so I hope it is clear that if it is less than equal to 0, then it is a mistake. Okay, then as it is a mistake, we have to update our weight vector. And the perceptron update rule was wt minus 1, the current weight vector, plus x times y. Okay, x is the data point, y is its true label. Okay, now we will compare the norm of the current weight vector and how it changes across the iteration. Okay, so we'll take the norm both side in this wt and the norm both side. Okay, so the norm square is same as the taking of that dot product of the vector with the itself. So this is the weight vector here, updated vector, and we are taking the dot product of this vector with the itself. Okay, now this calculation of the simplification of this is same as like how you do in general. Okay, so that is first we will multiply this and this, so it will becomes the norm square of wt minus 1. Then you can multiply these two. Okay, so that will become 2 times y times wt minus 1 transpose x. Okay, as y is a scalar, so you can move around this term. Okay, and when you do the final product of these two, then it will become norm x square times y square. Okay, the y square is equal to 1 because we have the labels either plus 1 or negative 1. Okay, so this is same as just norm of x square. Then we know that the norm x square has an upper bound of r square, so that r square will come, and wt minus 1 transpose x into y would be less than equal to 0. Okay, now why it would be less than equal to 0? Because the perceptron has made many mistake. Okay, so the final thing that we will get is the upper bound, that the updated weight vector has an upper bound of the norm square of the weight vector that was there before plus r square. Okay, and then if we continuously apply it, then for wt it was wt minus 1 norm square plus r square. Then we can similarly do the same thing for wt minus 1 also. So we'll get norm square of wt minus 2 plus r square plus r square. And if we keep doing this, then because we have done till t updates, for t times r square. Okay, because norm square of w0, as we initialize with the 0 vector, so it is 0. So it would be just t times r square. So this is the upper bound that we will get. Okay, the main points to remember here is this inequality and the final one. Okay, so these two are the main thing that you should remember from the proof of convergence. Okay, in doubt? Okay, the final bound that we'll get, yes, Karthike.
This bound,
Hmm.
I'm not able to, because we say the L square, L is a number of mistakes, right?
This t
And
is the
then,
number, yeah,
yeah, and then
r.
because here the lower bound has L square and the upper bound has L and then R square. So here, if the number of mistakes are too high and the R is a bit low, means the data points are so concentrated between very R of 10, say for example,
Hmm.
and the mistakes are more, then how?
And now see, this is okay. So T here is the number of updates that you have seen. Okay. R square is the data points which is further away, or the with which you can say the farthest data point. Okay. And on the left hand side is the current updated weight vector. Okay. So the norm square of that would be less than or equal to the number of mistakes times the R square. Okay. This is the upper bound that we are setting up. Now, this would enforce, it's not like the perceptron will go till this much mistake. Okay. It will terminate way before also. Okay. It depends upon the data set. Okay. So it's not like it is the final thing that it will go. It can terminate way before that also. Okay.
Okay. Okay, thank you.
Okay. So now we will discuss the lower bound. So we will look at the relation between the optimal weight vector, okay, and the weight vector that is the updated weight vector produced by perceptron. Okay. And we will use dot product to measure this relationship. Okay. A dot product between the optimal weight vector W star transpose and the weight vector updated at some t iteration in the perceptron. Okay. And again, we can write this weight vector as WT minus 1 plus XY. Okay. The above term simplifies as W star transpose W T minus 1 plus W star transpose X Y. Okay. And because this is the optimal weight vector, okay, and our data set is linearly separable with some gamma margin. So we know this term is bounded with that for all the data point, this would satisfy greater than equal to for the gamma. Okay. All the data points satisfy the condition that W star transpose Xi Yi is greater than equal to gamma. So we can write the above term in the form of inequality as W star transpose Wt minus 1 plus gamma. Okay. Now, if we again do the recursive thing, then we will get this as the final form. Okay. W star Wt is greater than equal to T times the gamma. Okay. As initially we will reach to the W naught, which is 0 vector. Okay. So this term will vanishes. Okay. So we'll just left with T times gamma. Okay. Same thing that we are doing here. If you do this recursively, okay, you will reach to this conclusion. Okay. Now we have to do some manipulation here. For that, we will use Cauchy squares inequality and the assumption that the norm of the W star is equal to 1. So the Cauchy squares inequality tells that the norm of the weight vector, okay, multiplication of the norm would be greater than equal to the dot product between them. Okay. And because we have take the assumption that the optimal weight vector has norm equal to 1, so we'll get this result that the norm of Wt would be greater than equal to W star transpose Wt, which is exactly this. Okay. So we'll put this result here and we will finally get norm square of Wt. Okay, if you do the square both sides, that is T square dot gamma square. We are doing square here because in the upper bound also we got the square. Okay. And of course, squaring both sides will not change the inequality sign. Okay. And if we combine both the sign, both the bounds, upper and lower, then we will get that at any iteration in the perceptron algorithm, the norm square of that is bounded by T square times the gamma square as a lower, and the upper bound is t times r square. Okay, and from that we will get t would be less than equal to r square by gamma square. Okay, r is the bowl, you can say, in which all the data points will lie, and gamma is the margin. Okay, again I'm saying that this is not needed or not necessarily to be true that perceptron will make this much mistake for sure. Okay, it can terminate way before that also. Okay, this is just the bound that it can set, and from this we can conclude that for a data set which is linearly separable with some positive margin, perceptron algorithm will always converge. Okay, and this bound is called the radius margin bound. Okay, so from the proof of the convergence of the perceptron, you should remember this radius margin bound. Okay, uh, the lower bound that we had arrived here. Okay, and from here this inequality that we have used. Okay, these 2-3 things you should remember. So any doubt in the proof of convergence? Okay, so the same thing that I said, that in about the bound that is written here, that WT is the weight vector after T updates. Okay, and another way of saying WT is that weight vector after the perceptron has made T mistake. Okay, each update is mapped to one mistake, and the total number of updates to the weight vector is bounded by r square by gamma square, because the total mistake Sm is the total number of updates. Okay, and for that we can say that the perceptron has to correct at most r square by gamma square mistake. Okay, and because it will be a finite quantity, perceptron algorithm will converge. Okay, so we will illustrate one example. Okay, so we have this data set, okay, which is of order d cross n. Okay, so each column is our data points, and we have a label vector, and for the perceptron algorithm we will cycle through the data points from 1 2 3 4 5. Okay, in the given order. So if we first plot the data points, this is how we have given the data points. X1 X2 are the positive class or the green class, X3 X4 X5 are the negative class or the red data points. Okay, so one can see that the data set is linearly separable with some margin. Okay, and now we will start. So our initial weight vector is 0. Okay, so because W that we are starting with is the 0 vector. Okay, now if you are going to take the dot product of each data point with this weight vector, it will always give output as 0. Okay, and that is the tiebreaker condition, and we have taken the convention that in the case of tie we will predict the output as positive 1. Okay, so that means for each data point here this weight vector will predict the output as 1. So it will correctly predict for x1, for x2, but for x3 it is a mistake. So x3 is the first data point where it will encounter it as a mistake. Okay, so the first mistake is made at x3 comma y3. So this is where the first update will happen. W naught, the initial weight vector, times x3 y3. So x3 was -1 -3. Its corresponding label is -1. Okay, so that's why this negative sign is here, because of the label of the data point. Okay, and if we simplify it, we will get the updated vector is 1 3. Okay, so if we plot the vector, okay, this is where the 1
Sir,
3
one
vector.
in the sir, one in the
Uh,
superscript means iteration, right? One W1.
yeah, this is the iteration. This is the iteration. Okay, so this is the vector that you will get, and the W transpose x equal to 0 line is this. Okay, now of course we can geometrically see that this is not correctly identifying all the data points. So we'll start cycling through the data points. Okay. We went till 3. Okay. So that means our next data point that we will use is x4. Okay. But clearly one can see that x4 will be a mistake. Okay, because it is lying in the direction of weight vector. So the predicted label for this data point would be 1. Okay, but that is the geometrical way of checking. But if we want to check it mathematically wise, our vector is 1, 3, and x4 is -1, 2. Okay, now if we take the dot product of these two, I get -1 plus 6. Okay, that is 5. And as it is greater than 0, so the predicted label for this data point would be positive. Okay, while the true label is negative, so it is a mistake. So the next update will happen at x4. Okay, so the vector which make mistake is 1, 3. The data point at which it is a mistake is -1, 2, and the true label of the data point is -1. One thing to remember that we will be using true label. Okay, for the update. Okay, so that's why this negative sign is here. On simplifying, we will get the new vector, weight vector is 2, 1. Okay, so if we again plot it, this is the vector that we will get. Now one more thing, that remember that x4 was the mistake. Okay, and with respect to x4 we have updated our weight vector, but still the x4 is incorrectly classified, because initially at the case of tiebreaker we are taking the output as positive. So still the x4 is predicted as, or it is falsely predicted. Okay, it is a mistake. So it is not necessary that if you have used, okay, so if you have used your weight vector for the mistake, okay, at some data point it is making a mistake and you are updating it, then it is not necessary that the updated weight vector will be correctly classify the data point for which the previous weight vector is making mistake. Okay, as you can see, this is the new vector, but it is still not correctly classifying the data point x4. Okay, so we have gone till x4, so we'll now resume with x5. Okay, so from geometrically we can say x5 is correctly predicted. So we will again start with x1. X1 is correctly predicted, x2 is correctly classified, x3 is also correctly classified because it is lying in the opposite direction of the weight vector. X4 is not correctly predicted. Okay, so it is a mistake. So again we will be using x4 to update the weight vector. This is the current weight vector 2, 1. Okay, x4 is -1, 2. Okay, and the label for the data point is -1. Okay, simplifying this, we will get the weight vector is 3, -1. Okay, so this is the 3, -1 weight vector. Okay, and this is the linear classifier boundary that we will get. Okay, another one assumption that, or conclusion that you can make from here, that it is not necessary that with each iteration in the perceptron algorithm the number of mistakes will decrease. Okay, this is also not necessary in perceptron. So we have cycled till x4, so we'll resume the cycle from x5. X5 is correctly predicted, so we'll start with x1 again, but this time x1 is not correctly predicted. Okay, so another conclusion that we can make from here, that even though the x1 was correctly being predicted from the first 3 weight vector, this time this new weight vector has predicted it as false. Okay, so now the update vector that we will be using is x1. So w3 was 3, -1. x1 is 1, 4. Okay, and the true label of the data point is +1. Okay, simplifying this, we'll get the new weight vector. Okay, so this is the new updated weight vector. So we have come till x1. So we'll resume with x2. And x2 is a mistake. Okay. So we'll use x2. The W4 was 4, 3. X2 is 1, -2. And the true label of the data point is 1. Okay. So on simplifying this is the new weight vector that we will get. And this is the weight vector that we call. Now, even though we can see from geometrically that it is correctly predicting all the data points, but to terminate our weight perceptron, we have completed till x2, so we'll resume the cycle from x3, and we have to again come till x2. Okay, and only then, as we will not encounter any mistake, we will conclude that our algorithm has terminated. Okay, so this was one full example. Okay, some conclusion that we made. So it was first thing that it is not necessary for the perceptron algorithm that after each iteration the number of mistakes will decrease. Okay. Second thing that it is not necessary that if for any data point xi yi it is making a mistake, then we will update the weight vector. Then the new updated weight vector has to correctly classify the data point. It is also not necessary. Okay. Third point that in a perceptron algorithm, if a point was being correctly classified by some weight vectors in the iteration of the perceptron, okay, then it is not necessary that in the future iteration of the weight vector in perceptron, also this weight vector, this data point would be correctly classified. Okay.
Sir, what was second point?
Second point was okay. What if for any data point xi yi, okay, if it is a mistake, okay, with the current weight vector, and you update the weight vector, okay, then it is not necessary that the updated weight vector would correctly classify your data point, okay, for which it was previously making the mistake. Okay, that we have seen maybe here somewhere, right? uh, Here the x4 was the mistake in this weight vector. Okay, x4 was the mistake, so we use x4 to update the weight vector. But the new weight vector is still miscorrectly classifying the x4. Okay, so this was the second observation. One was that it is not necessary that maybe I will write. One point, it is not necessary in perceptron that after each iteration number of mistakes will reduce. Okay, there's no guarantee in the perceptron that after each iteration the number of mistakes will reduce. Okay, second point, if for a data point xi yi, if it is a mistake by wt, then it is not necessary that wt plus 1 will correctly classify it. Okay, and the third point, if a data point xi yi was being correctly classified by uh, till some iteration t in perceptron, Next question for you. If a data point XY was being correctly classified till some iteration T in perceptron, then okay. So these are the three observations. Okay. So anyone has any doubt till now? Any of these observations and the example and perceptron? No?
Sir,
Yeah.
can you once just explain that part where we took W transpose y less than equals to 0? That one, I sometimes get confused in that.
Mm,
Initially,
yeah, I remember. You mean here?
yes.
Yeah. Okay. So remember that we are making one assumption that for all our data point is linearly separable with some gamma margin. Okay. So that we can mathematically write it as W transpose Xi time Yi would be greater than equal to gamma. Now, why this would be true? That if W transpose Xi is greater than equal to 1, okay, if it is if it is greater than 0, okay, that is it is positive, okay, and if the label is also positive, okay, that is it is correctly being classified, okay, and if W transpose X is negative and its label is also negative, okay, then this negative and this negative will also become positive, then it is also correctly classified, okay. Only when either W transpose X is greater than 0 and its label is -1, okay, or the another case, that W transpose X is less than 0 or the label is +1, okay. That is the case where the mistake will occur, okay, that the predicted label, as because it is greater than 0, so it will predict it as positive while its label is negative, okay. So the overall quantity would be negative, okay, or the case when W transpose X would be less than 0, so it will predict it as negative while the label is positive. So again this overall quantity would be negative, okay. So if your W is correctly classifying, okay, remember that W star is the optimal weight vector that correctly classify all the data points, okay. So for that this quantity would always be greater than equal to some okay, some 0, okay, but because we are also taking one more assumption that our data set is linearly separable with gamma margin, so for all data points this would be greater than equal to gamma, okay, because W star here is the optimal weight vector, okay. But while doing perceptron, okay, in the perceptron iteration you might encounter any mistake, okay, and if you encounter a mistake, for that the W at that some t minus 1 iteration transpose xy would be less than equal to 0, because either this would be greater than 0 and the label would be -1, okay, or either this would be less than 0 and the label would be +1, okay. So the overall will become negative. Did you get it now?
Yes, sir. Yes, sir. Thank you.
Yeah. Anyone, any more doubt? Okay. For Anthem, 50, you can say 50% of the question would be from week 9 to 12, okay, the last 4 weeks, and the remaining 50% you can expect from the first 8 weeks, okay. Now, one remark that there may be multiple valid weight vectors, okay, and perceptron returns any one of them. And depending upon how you cycle through the data points, it may return a different weight vector. Okay. Like for this example, there are different weight vectors that are possible. One is, of course, the y-axis itself. Okay. So as we have already studied the week 10, so we know the effect of the march. Yes, Karthik.
Can you please come again on that remark?
Yeah. So it was that there are multiple valid weight vectors for any linearly separable data set with some positive weight margin. Okay. Like for this as an example, there are different weight vector that you can choose. Okay. And with that, you will get a different boundary. So like this, okay, I mean this, okay, this. Okay. So there are different possible. Okay. And perceptron can run any one of them. Okay. But first thing that it is not necessary to be the optimal weight vector that the perceptron will output a optimal weight vector. Okay. And another thing is depending upon how you cycle through the data points. Okay. Like for this example, we are cycling in this order x1, x2, x3, x4, x5. Okay. If I reverse my order like perfect, x5, x3, x4, x2 like this. Okay. Then it might return a different weight vector. Okay, that weight vector will also classify all the class correctly, but it might be a different weight vector than this one. Okay.
Okay. And this, the number of mistakes based on this, if the gamma is very less and close to origin,
Hmm.
and then R is very high, the mistakes are really huge.
Hmm.
Even we have a bound.
Yeah.
So
And
what
that is a fine.
advantage?
That is a atmos bound. It is not necessary that perceptron will make that much mistake. Okay. It might convert way before than that. Okay. And usually it converts before than that only. Okay.
We cannot find that point.
You mean the exact number of mistakes that it will make? You mean?
No, not exact, but this is as we see giving this number r square by gamma square.
No. We
It
can just
can
tell that.
go a little bit. It's not
No.
far because we are talking like it will find much before this number. So we cannot go and find that bound. Is it
No.
not possible?
No, we can just tell that it can make at most this much mistake. We cannot exactly tell how before it can terminate. Okay. Just it will not make more than that mistake. Okay. That's the at
Okay.
most.
Okay. Okay. Thank you.
So one case of the margin. Okay. So from week 10, we have studied that our goal will becomes to maximize the margin. Okay. So the if for any linear classifier, if it has a maximum margin, then it will predict better on the unseen data points. Okay. So the larger the margin, the better our model. Okay. So this was one experiment that demonstrated the effect of the margin on the number of iteration needed to converge. Okay. And T refers to the number of updates to the weight vector. And one thing, it is not the upper bound that it is the actual number of updates that it will take. Okay. So if here D is the margin. Okay. If you have a margin of 1, okay, then only in one iteration it is converging. Okay. If you have a margin of 0.5, then it is converging in 2 iteration only. Okay. And if the margin is 0.1, okay, that is you can say the data points are very close, then it is taking only 7. Now in this, the data points might look like that it is not linearly separable, but there's some margin of 0.01 till it is just taking 44. Okay. So it is not going till the actual bound that it is, okay, but it is terminating before than that, okay. But we cannot find the actual, but we can just say that it can make at most this much mistake, okay. And the observation that we made is as the margin decreases, the number of updates increases. So of course our goal will become to maximize the margin, okay, because we cannot do anything with the R square, okay. That is something the data point will have, okay, but we can try to maximize the margin, okay. That we do in the FVM case, okay. Okay, so this is all about perceptron. Any doubt?
Sir, I have doubt in 1PYQ. Can I share my screen?
Okay, that I will take it at the end, okay. From
Okay.
conceptual, do you have any doubt?
No, sir, no any doubt.
Okay. So next thing is the logistic regression. So in Perceptron, we are going with a very strict assumption of linear separability, okay. And because of that, it is very strict. We can turn this into a little bit soft and introduce probability in our model, okay. So logistic regression is one such model, okay, which will, okay, use the account of conditional probability, okay. That is given the data points, the probability of y equal to 1 is sigmoid function value of W transpose X, okay. In the perceptron, we are directly taking if W transpose X is greater than 0, okay, then it will classify it as 1, okay, else it will classify it as -1. And logistic, we are going with the probability, a little bit soft measurement for that, okay. That is the probability of y equal to 1 given X is sigmoid function value of W transpose X. And the sigmoid function is 1 upon 1 plus e power minus z, okay. This is called the sigmoid function or the logistic function, okay. And W would always be in the same dimension in which our data points are lying, okay. The properties of sigmoid is it will lie between 0 and 1, okay. So generally we use a threshold value to determine our class, okay. So that is at what threshold value should our this probability be above to classify our data points to the class 1, okay. So the general threshold value is 0.5, that is if the probability of y equal to 1 given X is greater than equal to 0.5, then the model output class is 1, else the model output class is 0, okay. One thing to note here is we are taking here label is 1 and 0, okay. So more formally we are defining that if the sigmoid function value for W transpose X, if it is greater than equal to 0.5, then it would be 1, else it would be 0, okay. This is the general 0.5, okay. By default or by convention we take, it can be any other value also, okay. It depends upon the case for which we try to find, okay. Now we will first discuss more on the sigmoid function, okay. So one thing was that sigmoid function lie between 0 and 1, okay. Look at the brackets here, it's small, okay. So that means 0 and 1 are not included, okay. So don't touch 0 and 1, okay. The sigmoid function, okay, it might be there, yeah, okay, yeah, okay. It won't touch 0 and 1, okay. It will be a asymptote to the x-axis here and the line 1 here, okay. It will not touch 0 and 1, okay. It will be between 0 and 1 only, okay. And the way you define sigmoid function for a number is sigma of z equal to 1 upon 1 plus e power minus z, okay. Yes, send out,
Oh, is the screen visible to all? Like from my end, oh, now it's visible.
okay.
Sorry.
Visible.
Some useful properties of sigmoid function. As z tends to infinity, the sigmoid function value at z would be tends to 1. As z tends to negative infinity, sigmoid function value of z will tends to 0. Okay. And at the point 0, the value of sigmoid function is 0.5. Okay. And if z value is greater than 0, then sigmoid function value at z would be greater than 0.5. And if it is less than 0, then it would be less than 0.5. Okay. One small result that sigmoid function value of negative z is equal to 1 minus sigmoid function value of z. Okay. The way you can prove this is sigma of negative z is 1 upon 1 plus e power z. Okay. The negative and negative here will become positive. Okay. Then you can divide the expression in the both numerator and denominator by e power z. Okay. If you do that, then the numerator will become 1 upon e power z. So it will become e power negative z. Okay. For the denominator, it is 1 plus e power z. If you divide it by e power z, then it is 1 upon e power z plus e power z by e power z. Okay. 1 by e power z is e power negative z, and this will become 1. Okay. And I can write it as 1 minus this. Okay. And this expression is nothing but sigmoid function value of z. Okay. So this is the result that sigmoid function value of negative z is equal to 1 minus sigmoid function value of positive z. Okay. And one more result is about the derivative, that the derivative of the sigmoid function is equal to the derivative of equal to the sigmoid function value at z times 1 minus sigmoid function value at z. Okay. It's the chain rule that you can apply here. So any doubt in this?
Sir, where we need to use this derivative property?
We will be using this when we will try to use the MLE later. Okay. We will see it here.
It is not covered in this course, I think.
It is covered. We will be computing the log likelihood. Okay. So that is basically the cross entropy loss. Okay, that will come from here only. Okay. So we will compute the log likelihood for the function. As we have probability, so we have to estimate the parameter for that. And best way is we will use the MLE. Okay. So we'll assume that the labels are drawn independently. Okay. So in such that case, the likelihood function will become product of the probabilities. Okay. For all data points yi given xi. Okay. So our probabilities are defined in the form of sigmoid function value. Okay. So for a data point, if the class is 1, the probability is sigma I. Okay. And the interpretation of this is, if sigma I is 0.75, then the model believes that there are 75% chance that the xi belongs to the class 1. Okay. And the probability that it belongs to class 0 is just nothing but 1 minus sigma I, that is 0.25. Okay. And the actual label for the data point is y. Okay, which is 1 or 0. So the predicted label is given by sigma I. If sigma I is greater than some threshold, then we will predict it as 1. Else, we will predict it as 0. Okay. But this piecewise function we cannot plug in directly in the MLE. So we will use this form. Okay. And this might look similar. Okay. We have done something the same in the case when we were predicting the estimate for the P probability for the Bernoulli, right? It's just that in place of sigma I, it was P. Okay. So sigma I yi times 1 minus sigma I 1 minus yi. Okay. I hope it is clear till now. Okay. Then just that we'll substitute this sigma I yi times 1 minus sigma I 1 minus yi. Okay. So in the MLE, next step that we do is take the log. Okay. So by taking log, this product will turn into summation. And it will become yi because it is in power, so it will come in front. Yi log sigma I plus 1 minus yi log 1 minus sigma I. Okay. And this sigma is same as sigma of W transpose xi. Okay. Till now, is it clear? Next comes the cross entropy loss. Okay, that we will derive from here. Okay. The cross entropy loss, you might have heard this term in the week 12, okay, in the neural network. Okay, so that is actually coming from here. Okay, when you take the log likelihood for the logistic regression while doing the MLE, okay, the negative of that log likelihood, you can view it as the loss function. Okay, and it is called as the cross entropy loss. Okay? So if you take the negative of this, that you can view it as a loss, because in the negative case you want to minimize that. Okay, and loss is something that we try to minimize. And this negative log likelihood is a convex function. Okay, and because of this convexity, the logistic regression will have an optimal weight vector for any given data set. And this is independent of the data being linearly separable or not. Okay, this is an important point. Okay, that the logistic regression always outputs an optimal weight vector. Okay, it is not, and it is independent of the data. Whether your data set is linearly separable or not, it will always output a optimal weight vector. And the reason for that is this, because this negative log likelihood is a convex function. Okay. Any doubt till now? Okay, the next steps are just taking the gradient. Okay, now here we will be using the properties that the derivative of the sigmoid function is sigma z times 1 minus sigma z, and the derivative of W transpose x is just x. Okay, so here we have this log term. Okay, so if you take the derivative of this, okay, it will become 1 by, right? The log of x, the derivative of that is 1 by x. So 1 upon sigma W transpose x. Then due to chain rule, you have to take the derivative of this term. That is sigma function derivative. And that we know is sigma of W transpose xi times 1 minus sigma of W transpose xi. And then again we have to apply chain rule for this. Okay. So the derivative of this W transpose xi is xi. Okay. So you are applying just chain rule, then chain rule, then chain rule 3 times. Okay. First for the log, then for the sigmoid, and then this inner part, W transpose xi. Okay. So this was the derivative for this first term here. Same thing you can do for the second term. And then it will become 1 minus W transpose xi, because it was log of 1 minus sigma W transpose xi. So for that derivative would become 1 upon 1 minus W transpose xi. Then the inner part. Okay. This negative sign is coming from here. Okay. So when you take the derivative of this inside, the negative sign will come. Okay. Otherwise, the derivative is same. That's sigma of W transpose xi times 1 minus sigma of W transpose xi. Then the inner derivative W transpose xi, that is just xi. Okay. Now this cancel out. So it will be just yi times 1 minus W transpose xi times this xi. And this will cancel out. it will be negative, the negative sign from here, and we have break down the summation here. 1 minus yi, okay, and sigma w transpose xi, xi. Okay. Now, if you simplify this term here, first of all, this, it is yi xi minus yi sigma w transpose xi xi. Okay. And this term here you will get is sigma w transpose xi xi minus yi sigma w transpose xi xi. Okay. Okay, there's one more negative sign, so this negative will become positive from that. Okay, because of this negative sign, okay, here you will get negative, and here this negative will become positive. Okay, so you can cancel out these two also. Okay, so this is the term that you will left with. Okay, these two. So you can take the xi common from here, and what you will left with yi minus sigma w transpose xi. Okay, and that is what written here. Okay, and we are replacing this sigma w transpose xi with the probability that we got. Okay, so this is the final result that we will get. Okay, now the main thing about this result is this y hat minus sigma I. Okay, this you can treat it as some kind of error in the prediction, because remember yi is the true label. Sigma I denotes the probability of the data point belonging to class 1. Okay, so if yi, let's say for example, is 1 and the model's probability is sigma I is 0.7, then the error in the prediction is 0.3. Okay, so the gradient of this MLE that we have taken is nothing but the error term yi minus sigma I times the data point. Okay, and that you sum for all the data points. Okay, so the larger the error, the more contribution for a data point towards the gradient. Okay, else if the error is very less, then the model is already doing a good job for classifying the data points. Okay, and such a point won't disturb the gradient. Any doubt in this derivation part? Okay, I guess this is the final. Yeah. So the final thing is gradient Sn. Okay, so as we have computed the gradient of the log likelihood, okay, and we have seen that we cannot get a closed form solution. Okay, because what we stuck is here. Okay, so we are not able to get any closed form solution for the W star. Okay, so we have to resort to some optimization technique, and one such choice is gradient Sn. Yes, Ravi. Any doubt? Sorry, if you are saying something, I am not able to hear you. Okay, maybe you can write it in chat. Okay. So we are going here with the gradient ascent because what we are trying to do is maximizing the log likelihood. Okay, so we are going with the ascent, not descent. Okay, and for that the update is Wt plus 1 equal to Wt plus eta times gradient of log likelihood. Okay, and the gradient that we got is summation from I equal to 1 to n yi minus sigma I times xi. Okay, this was in terms of vectors. In terms of matrix x, okay, this is what you will get, x times label vector minus the probabilities of all. Okay, and Since this log likelihood is a concave, okay, gradient ascent will converge to the optimal weight vector for a suitable choice of the learning rate eta. Okay. So one was not given to you that gradient descent is not used to learn the weights of logistic regression model in practice. Okay, there are different derivative method that we use. One such choice is Hessian. Okay, for the second derivative. Okay, so this was the final point on the logistic regression, and that covers the week 9. So anybody has any doubt in logistic or perceptron? Clear to everyone?
Sir, what does that closed form solution actually mean?
Closed form solution means like, for example, in the simple linear regression, if you remember when we take the gradient of the SSE function sum squared error and set it to 0, we got the closed form solution for W star, right? As this XX transpose pseudo inverse XY, right? This was the closed form solution. Okay. In the case of sorry, it is okay. In the case of estimating the probabilities estimator for the Bernoulli, we got the closed form solution as the fraction of ones, right? It was like nh by n for the p hat in Bernoulli. Okay, so these are the closed form solution. Okay,
Closed in sense like is it closed between some limit or what?
no, it is, you can say, in kind of like in which you don't have to do any iteration method like here gradient descent ascent. Okay, you can just directly plug in your weight vector in some kind of formula type you can think of. Okay, that like
Okay.
in the linear regression, you have the formula like XX transpose pseudo inverse XY. If you put your data points label, it will give you the vector. Okay, you don't need to do the gradient descent, even though you can do because it is much faster in terms of computation. Okay, so that is what it is meant by closed form. Here we don't get any closed form. Okay, because you will stuck here. Okay, so you cannot do anything further. Okay, and that's why you need to go into the optimization technique like gradient descent. Okay, got it? Any more doubt? Yes, now I will take your doubt. Yeah,
Can I share, sir?
yeah, you can share. Okay, I will stop sharing my screen.
Sir, are you able to see my screen?
Yes.
So this is a question. Here we have to take x0 as a bias term, or what we have to do here?
X0. First of all, which term PYQ is this?
I didn't remember, sir. But
Okay.
it's based on perceptron, sir.
No, because it is taking W0, W1, and W2. So
Yeah,
it is
sir.
also taking the bias. Okay. So it
Yeah, sir.
might be, I think it is before September 22 term. Okay. Before September 22, there was a different syllabus for MLT. Okay. So in which we have also included the bias term also. Okay.
Yes, sir.
So
That was my
that is,
question. Because
if
if
that is,
we will make bias term, then it will be solved.
yeah, if okay, so that's why I'm saying don't go through the papers that are beyond before September 22. Okay. Start from the September 22. That is your,
One question, sir. One question also.
yeah. If you have any other question that you can.
Let's open this.
This is the same.
This question.
Can you zoom more? I'm not able to view it properly. Can you zoom more? No, we are not going to do week 10 today. Okay, consider a logistic regression that has been trained for a binary classification problem. After two data points from the training, the model state vector and these symbols are drawn. Symbol, okay. Are the probabilities output by the model for the two data point? If sigma 2 my and are treated as error in the prediction for the data, compute the following quantity. Okay, note that the probability output by the logistic regression is okay. So figure is drawn to scale. Okay. So see sigma I is what? Sigma I is the probability of y equal to 1 given x. Okay. So that is sigma of w transpose x. Okay. You have
Yes,
given
sir.
the w vector. You have given the x1 and x2 and okay. So from that you can get the sigma I value, right? Okay. And you can
Yes,
get
sir.
the you can from the figure you can also get the true label also, right? For the data point. It is already given.
Sir, but the level of y1 would be -1.
Y1, the label of x1 you mean? Yeah, label of x1 is -1 and label of x2 is positive.
And what's about y1 and y2?
Y1 and Y2 are the true label. Okay, so labels are in 1 and 0. Okay, so that means the label of the data point x1. Okay, that means the value of y1 is 0, while the value of y2, that is the label of the data point x2 is 1. Okay,
Okay, 1. Mhm.
because it is given in the last line of the first paragraph. The symbols plus corresponding to the label 1 and the negative corresponding to the label 0.
Sir, but the weight vector is not given here, so
It is given, right? It is drawn, and it is also given that the figure is drawn with the scale. Okay, so weight vector
okay,
is
sir.
1, 1.
Okay, sir. Thank you, sir.
Okay,
Got it.
yeah. Any more doubt?
No, sir, no any doubt.
Okay. Anybody has any more doubt? It can be from any other. Yes, Karthika.
Oh, what is the plan for week 10, 11, 12?
That I guess that session will happen on Friday. Okay, from 6 to 8. And for now, if you want to revise week 10, the week 10 tutorial has been released. Okay, and you can check out from the portal. Okay, that covers the SVM part. Okay, so you can revise that from there also till then.
Okay, thank you.
Sir, SVM up to soft margin or only up to hard margin?
Sorry, can you repeat?
That part, that tutorial covers SVM only up
Yes, it
to
covers.
soft.
Yeah, it covers only hard margin case.
Okay.
Okay. It is just the week 10 tutorial. Okay, so it covers only the hard margin, not the soft margin. Okay. Soft margin SVM tutorial in the week 12, that is week 11 and 12 tutorial, we are not able to record before the ET. Sorry for that. Okay. So because of time limitation, we are not able to record it before. Okay. But you might have to work around with the summary slides that is available in the master folder till then. Okay.
Okay, sir, and please kindly upload that week 12 video as soon as possible.
Yeah, I have messaged it. Just let me check once if I have messaged them. Okay. As soon as I will get any response from the team, okay, I will either share it on the discourse. You can check out the discourse. I will share it on the discourse. Okay.
Okay.
Okay. Anyone has any? Yeah.
The total number of questions for the intern, how much generally?
Generally, it is you can expect around 25. That I will say. Okay.
25.
Yeah.
Okay.
And
Okay.
maybe you can look out the past.
And 50% and 50%?
Yeah. Okay.
Okay. 50% for week 1
And
to 8.
50% for the last. Can you
And
share that? Okay, discourse.
Hello,
Discourse.
sir.
Yeah. Yes.
Hello.
Hmm.
Actually, if suppose that the optimal weight vector is given in the question,
Hmm.
and in a hard margin, we have to find the decision boundary. So we have to use 1 upon normal of W weight vector or 2 upon.
No, if the question is asking for the decision boundary, it is W transpose X equal to 0, right?
No. Distance.
Okay, distance between the hyperplane. So it would be 2 by norm of W.
Okay, sir.
Okay.
Okay, sir.
Don't use norm W square. It is just 2 by norm of W.
No,
And
sir.
sir,
I thought 1 upon W norm square.
No, distance between two supporting hyperplane is 2 by norm of W.
Okay.
Okay.
and sir, distance between the separator and one supporting hyperplane would be 1 by norm of W, right?
Yeah, yeah. On one side, it is just 1 by norm of W.
Okay.
Okay. So you can watch the tutorial. Okay. So same thing has been explained there. Okay. You got that norm W. Okay.
Yes, sir. Yes, sir.
Exactly. Okay. Okay. Any more doubt, anyone? Okay. So we'll end the session today. Thank you all for joining. Good night.